This is video number 18 about parametric curves. I've been using parametric curves to try to model motion, and recently we've been focused on calculus ideas related to that motion. That if you create two functions, two graphs, one of them called distance of t, which gives you how far you've traveled at time t, after time t, and another one called speed of t, giving you the instantaneous speed at every moment in time, that you can say two calculus facts, one that I've highlighted here and another one that I have not highlighted here. The one that I did not highlight here says the value of the speed graph is the slope of the distance traveled graph. And the one I have highlighted here is that the area under the speed graph, starting from time 0, gives you the value of the distance traveled function. I want to illustrate that fact once more here in this video. In the last video I also introduced the idea of a position vector. A vector is an arrow, and position vectors are arrows that are based at the origin. They start at the origin and their tips point at the location of the person as they move. And one new thing I want to do in this video is talk about a special notation, actually a couple special notations for these vectors. Alright, so in the last video we used this particular function h of t equals t cubed at the very end to model a motion that starts out slow and ends up going faster. I think to emphasize the calculus facts again in this video I will change the example. Instead of a t cubed I'll do a square root of t here. Actually, this particular kind of motion, h of t equals square root of t, ends up being an impossible kind of motion because it would imply an infinite speed initially, but maybe it's close enough to be a halfway decent model in a situation where you start out fast and slow down. So now that's the opposite situation. We're starting out fast and we're slowing down. The graph in the upper right here tells you your y coordinate as a function of time. The graph in the lower left tells you your x coordinate as a function of time. You want to look at the graph with your head turned at a 90-degree angle to the right. Again, we see the motion up here. The black dot is where the person is located. This black arrow pointing from the origin to the black dot is the position vector for that motion. Notice the position vector changes. It's an arrow that changes both direction and length. Okay, so it's a changing arrow. It really is a function of time. And then down here on the right, we've been emphasizing the calculus-related facts to these graphs. The blue graph down here is the distance traveled function. Notice we travel 5 units of distance. It's a little hard to tell there, actually. 5 units of distance, that is, 5 units there. It goes from 0 to 5 as t goes from 0 to 1. Its slope is very high to begin with. You're moving pretty fast, in fact, again, infinitely fast initially at time 0, even though that's not something that can happen in real life. And then you slow down because the slope gets smaller and smaller. The value of the red graph, the speed graph, which is about 4 here, is the same as the slope of the distance traveled graph at this point. If you measured the slope of this tangent line in magenta here, by doing a rise over run, you would get about 4. And then the second fact here, the area under the red graph, which actually goes up forever over here in this example, but the area does end up being finite, is the same as the value of the blue graph. This area, though it doesn't look like it because the scales are off, would end up being, it looks like around 2.5 to 3 or so is the value of this blue graph. Okay, if that went fast, you probably want to rewind and watch that again. What I'd like to do now is focus on the position vector ideas and the notation that I wanted to show you. And I think to facilitate that discussion a little bit better, I'm going to copy and paste this, manipulate down here. I'm going to put the paraplot here and get rid of the grid. So that'll allow us to just focus on the parametric plot along with the position vector. I'll make a bigger plot now so we can see just the motion along with the position vector. Again, what are we doing with this arrow, this vector? We are creating it in such a way that it's based at the origin. The start of the vector is always at the origin, and the tip of the vector is always at the location of the person as they move. This is a changing vector. It's changing both in direction and length. It is itself a function of time, and now I want to emphasize that with some notation. Go ahead and go to text mode here. The position vector starts at the origin and points at the location of the person as they move, which would be the point, going back to our notation we've been using, C of h of t, whose coordinates are f of h of t, comma, g of h of t. We've got these functions that I've created. If you're feeling lost here, you should go back and watch a bunch of old videos. This is my notation for the location of the person as a function of time. I guess I need an extra parenthesis here too. This is a point. First coordinate, second coordinate, f and g were simple functions that gave the coordinates initially for constant speed motion, and then the h of t was plugged in to change the speed. And then the c function is a point valued function. It takes a t, a number t as input, and gives you a point as output. Because of this, it makes sense to associate the position vector with this point. I'm not going to be real precise about what I mean by associate, but I'm just saying we're associating the position vector with the point, not just in the sentence here, but also notationally. We will denote the position vector by, first of all, we're going to give it a function name. The function name we're going to give it is going to be r. Why r? Well, it's actually pretty standard. And I said I'm following the book by John Rogoski here and using his notation, and he often uses the c function for the point valued function, and an r function, a function named r, for the vector valued function. When you see vector valued functions in textbooks, or here otherwise typed in some other way like in Mathematica, you will often see them non-italicized and bold-faced. And that's what I just did. I made it non-italicized and bold-faced. That's one way that you will see vectors specified in many textbooks, both physics and math. All right? By hand, you can't typically make this a boldface. You will often see teachers write it by hand as follows. Let me show you the palette here. I'll make it bigger. This kind of notation to put a half arrow above the vector, like this. So you would see a teacher by hand often do it like that. That's not the only way teachers do it, but it's the way I do it, and many teachers do it this way. Okay, since you can't really make a boldface by hand. And we will make this association a little bit more precise by saying we will write that, let me go back to small here. R of t equals, this equals might be with quotes. Okay, I'm going to initially write it as a point, f of h of t, comma, g of h of t. But I am going to make a change to this, two changes in fact. I am going to make this non-italicized and bold. I'm also not going to use parentheses here. Now if I put a literal equals here, like you see an equals there, that would make you think r of t is a point valued function, giving you a point as t changes. But it is a vector valued function. You get an arrow out as t changes, but this association between the vector, the arrow, and the point that it's pointing at is so clear, hopefully, it's a very natural thing to do, that we feel like writing an equal sign here even though it's not a point. But to specify that it's not a point, John Rogoski, not all teachers do this, but John Rogoski and I use a slightly different notation. We put sort of a less than sign instead of a left parenthesis, and then a greater than sign instead of a right parenthesis. So what you see here is special notation that does two things really. It emphasizes that the vector is not a point because we don't have parentheses around it, but it also emphasizes that there's this tight association between the vector and the point that it's pointing at. Okay, and the association is even broader than that, dealing with something called displacements or components. But that initially is the association we'll make, and I hope that makes sense. It's not a point, but it's very much associated with a point, and that's the reason for this notation.